everyone for having me. It's quite short notice, but it's exciting to give a talk there. I would have liked to be there with you at this beautiful place, but can't have everything. So yeah, I'm talking about the physical carbon pump in the Southern Ocean today, and I was asked to present myself a bit before, or I was told other people did that, so I thought I'd do the same thing. So I myself come from Germany, studied physics in Heidelberg, where I did my bachelor's and master's at this beautiful place there on the left. But I studied in Heidelberg, but I never really worked there, so I did my bachelor thesis in Southampton at the National Oceanography Center, and where my passion for oceanography really started. A beautiful place to live and work, so if you ever get the chance, you should try to go there. And I did a master's in Paris. That was partly for personal reasons, but it's also a good place for research. And I did my master thesis in biogeochemical oceanography, going away from physical oceanography to biogeochemistry, and at L'Océan, a nice lab. I mean, Linus and JB are there as well. And then I did a PhD again in France at the LSCE, a little bit south of Paris, and at the École Normale Supérieure in biogeochemical modeling of the Arctic Ocean, where I went a little bit more into polar oceanography, nutrient cycles, carbon cycle, acidification. And afterwards, during this PhD actually, I did a 10-month research stay in Brussels. So moving around again to work more on the land, ocean, aquatic continuum, so everything that goes into the ocean from the land via rivers and erosion. So all this moving was quite exciting. And afterwards, I left the French-speaking part of Europe to go to Bern, Switzerland, and to work more on global ocean and climate dynamics, still in the modeling part. So I'm not much of an observational oceanographer, but like to modeling and work more on the Southern Ocean and global ocean climate interactions. And I said I'm more modeler, but then I wanted to go once at least on a ship, so I applied for a research fellowship in the United States in Woods Hole, and went for 1 month into the Arctic Ocean. And on the left side you can see the ship. There we already out of the Arctic again, but it was exciting cruise with an icebreaker going in November in the dark through the ice, seeing polar bears. Kind of impressive, and the whole stay in Woods Hole was pretty nice as well. Here you can see where I worked, so also a nice place to go to. And now I'm back again in Switzerland, and I have my own project now for 5 years to work again on the Arctic Ocean ecosystem and how it's going to develop in the future. So I've moved around a lot, stayed kind of in Central, Northwestern Europe, but I try to see as many places as possible and work with as many different people as possible. And I think that has helped me a lot to gain my knowledge so far, to create a nice network and just to science with, I would say, friends by now. So kind of nice to move around and make new friends this way. So let's move to the actual subject and not talking about me. I'm talking about one of the greatest oceanographers, I guess, Wally Broker, and why do we care about the physical carbon pump. And I didn't know if I didn't hear all the other lectures, but there's always this kind of question: what drives the uptake of additional or anthropogenic CO2 from the ocean? And yeah, I think what people agreed on by now is that the importance of the physical pump is really the main driver of the uptake of additional carbon by the ocean from the atmosphere. And that the physical processes are the ones that are most important, and biology is important for the natural carbon cycle, for ecosystem stresses, and for a lot of things. But if you really want to know how much carbon the ocean is going to take up, it's really the physical carbon pump that is doing the main work and that we should concentrate on. And that's why I think it's important to talk about this today and to do more research about it. And if you look at the change in carbon since pre-industrial times, here an observational-based estimate from Christopher Sabine, the change in carbon from 1765 to 1994, we see that the ocean doesn't take up the carbon in a very homogeneous way. It's actually quite different at places, and we can see that the North Atlantic is the most intense carbon sink, but it's actually not the biggest carbon sink, because the area in the Southern Ocean is so huge that the Southern Ocean here is the biggest carbon sink in the ocean. And if we look at this in an integrated way from south to west, so you see different lines represent different models from CMIP5, and there's an observation-based estimate in black. And so if you go from left to right, you see how much carbon has been taken up until that latitude by the ocean. So you can see once we get out of the Southern Ocean here by around 30 degrees or 35 degrees south, we can see that already 40 to 50% of the entire uptake of carbon has been taking place. So this region here, or here, is really the most crucial part for the uptake of carbon. And in addition, what we can see as well is that these lines here evolve more or less parallel afterwards, and the biggest uncertainty in the uptake of carbon by the ocean also comes from the Southern Ocean, which makes it very complicated, because it's a very complicated region to simulate because of complex dynamics of the ocean circulation that climate models can't always resolve very well. And also observations are there are not many in the Southern Ocean, so that we have to rely on extrapolating observations and on using models. And if you look into the future, we can see here on the left side the uptake of carbon by the Southern Ocean, and on the right of the global ocean. And we can see that uncertainties remain high in the future. What we also see is that over the future, the Southern Ocean continues to take up around 40 to 50% of the entire anthropogenic carbon estimate. So this is the SSP 585, so comparable with these lines here. And we can still see that's 40 to 50% of this. So even over the future, the Southern Ocean remains the dominant carbon sink. And that's why we have to understand it better to know how much carbon the ocean takes up and how much carbon the Southern Ocean will take up. And why is the Southern Ocean such an important carbon sink? You probably have seen this plot. There's a plot that's looking a little bit similar to this plot, where you see the westerlies blowing and the Antarctic circumpolar current creating the Ekman transport to the north, pushing water away, creating the mode and intermediate water formation here and allowing old deep waters to come up back to the surface. And these upwelling waters, which haven't seen the atmosphere and the increase in carbon for decades and centuries, they can take up a lot of the new carbon that's in the atmosphere, which is happening here, and together with the warming, and then it's effectively stored below the subtropical waters in the southern hemisphere as mode and intermediate waters. So this dynamic here, driven by the current and the winds, really allows the Southern Ocean to take up more and more carbon over time, which allows it to be a continuous sink of carbon over the next decades and centuries. We also have the dense water formation here, but in terms of anthropogenic carbon or carbon uptake in general, it's not a big, it's a relatively small contribution. Most of it really goes into the dominant cell up here. And now if you look at the fluxes in terms of anthropogenic, what I talked about, so the new carbon and the natural carbon, we actually get two very different pictures. So if you first look at the right side, so the natural carbon cycle, we have this upwelling of carbon-rich water masses. So green having more carbon and red having less. And they upwell here, and then they lose a bit of carbon to the atmosphere because they are so rich after all the remineralization of organic matter has happened in the deep ocean. And then they can take up a little bit more, but the anthropogenic cycle is really completely immersed. As I said before, we have these waters that haven't seen the increase of carbon due to the Industrial Revolution and activity afterwards, and are still very low in anthropogenic carbon. And when they come up to the surface, they can take up all this new carbon and store it here below the surface. So it's actually two different pictures, which in total together create the entire flux, but this natural flux is stable and has an equilibrium in the global ocean with the atmosphere, but this one is the one that's changing. And this is why the Southern Ocean really can increase the ocean carbon inventory by this cycle of upwelling of low carbon waters, anthropogenic carbon waters, and storage then of high anthropogenic carbon waters. And when I say anthropogenic, there are different definitions around in the scientific world. What I mean is that all changes in the carbon cycle due to increasing CO2 and climate change. So it's not just the increasing CO2, but also the effect of climate on the carbon cycle. And as I said before, it's very complicated to observe and to model the Southern Ocean. And just to give you an example of this, here are estimates of global ocean biogeochemical models that are forced with observed atmospheric conditions of temperature, humidity, precipitation, and other variables, winds, for example. On the left and on the right, you see PCO2 products, which are extrapolations of a few observations in the Southern Ocean in space and time. And we can see the general picture that we have seen for the natural carbon cycle, the outgassing here in red, where water comes out of, or where the circular deep water upwells. And then a little bit more uptake here, where we have also subtropical waters coming down that cool down and then can take up more carbon, and then they sink together. And we see relatively good agreement in both estimates. Of the general picture, we have a good idea, but then if we look at the different estimates here of the different models and different PCO2 products, we see that this agreement falls apart a bit. And just to see how this total flux here decomposes again, to bring back the idea of the pre-industrial natural carbon flux for the outgassing and ingassing. And then we have the additional anthropogenic uptake that creates now this picture where we almost lose this outgassing here, because the additional uptake from increasing CO2 in the atmosphere becomes that large that the outgassing of natural carbon is almost suppressed. And in the future, this will go further down and only uptake will continue. So, this was why we care about the Southern Ocean, but how do we actually observe the Southern Ocean carbon sink? I already said that observations are sparse, but now we are going to have a little bit deeper look in how these observations are used, how they're extrapolated, and what uncertainties come with these estimates. So what kind of observations do we have? We have ship-based observations, like here the icebreaker from the British Antarctic Survey, and it's not Boaty McBoatface, it's Sir David Attenborough, although I would have preferred the other name, to be honest. And then we have bio-Argo floats, which are autonomous floats, like the Argo floats for physics, that you can furl into the ocean and that have sensors of different variables like pH, chlorophyll, in addition to temperature and salinity on there, and they float with the ocean currents. You can't direct them, so they just go with the water, and they can sink to 1,000 meters. And while they sink, they take continuous measurements, and then they move with the water again at this depth, and then they sink again to 2,000 meters and take measurements, and then move again a little bit around, taking measurements and coming up again, and via satellite sending these observations back to whichever research center operates that Argo float, and then it starts the same cycle again and again. So these kind of observational tools really increase the number of available observations, because they're not cheap, but relatively cheap compared to ship-based observations where you have to move a whole ship and crew down to the Southern Ocean. And they just cover a large range of the ocean by moving around autonomously. And then we also have sail drones that measure the partial pressure of CO2 in the atmosphere and in the ocean, and that also move around autonomously and driven by solar power, which is also kind of nice. And lately there are also observations coming from sailboats, from professional sailors going on races around the Southern Ocean. I think, what is the name? The Vendée Globe, where they go from somewhere in Europe down to the Southern Ocean, once around and then come back. And more and more of them are taking now equipment to measure the partial pressure of CO2 and then the flux of carbon into the ocean, and which helps a lot. And I will show later an example how just one additional cruise by a sailboat increases our confidence in the estimates of the air sea CO2 flux and the ocean carbon sink in the Southern Ocean. So all these different measurements are still point-wise measurements here that you can see on the upper left, where you have each measurement in a color with the partial pressure of CO2 measured there. We can see that in the Southern Ocean we have most gaps. So we have the North Atlantic quite well sampled, North Pacific as well, where we have most of the trading routes where ships can also take observations. Once we get to the Indian Ocean and the Southern Ocean, we have large gaps where we don't even have any observations ever taken. And to account for these gaps, the complicated or more or less complicated methods that can be used to extrapolate this data in space and time to come up with a total map of the partial pressure of CO2 in the ocean. And these methods go from simple extrapolation to complicated neural networks that are trained and that use different other mostly physical observations like temperature, salinity, but also chlorophyll, everything that you can measure with satellites, ideally, to extrapolate the partial pressure from the observed places to the non-observed places. And once we have the partial pressure of CO2 in the atmosphere, we can use this formula where we have the fraction of sea ice and most importantly the difference of the partial pressure of CO2 in the atmosphere and in the ocean. So if there's more CO2 in the atmosphere than in the ocean, we have a flux of carbon into the ocean. And if there's more CO2 in the ocean at the surface than in the atmosphere, it goes out. And then we can turn this map of partial pressure into a map of air sea CO2 fluxes. And we can see where we have high partial pressure, for example, in the upwelling regions in the equatorial Pacific. We have a lot of outgassing of carbon from the ocean to the atmosphere. And also we can see in the Southern Ocean, the small band here, where we have relatively high CO2, where carbon is lost from the ocean to the atmosphere. And this is the best way we can use observations at the moment to estimate our air sea CO2 fluxes. And there are several methods that do this, and that then the average can be used to get the best estimate. And then if you look like how the flux look like in the Southern Ocean, so here it's south of 35 degrees south, and we see an air sea flux anomaly with negative being into the ocean and positive being out of the ocean. And we have different estimates. The one that I want to concentrate on is now this neural network estimate from Peter Landschützer, one of the first observation-based estimates based on these methods that I just showed you. And we can see that the uptake of carbon in the Southern Ocean actually wasn't as linear as we would have expected. Because if you just look at the increase in atmospheric CO2, and the atmosphere would have expected just a slight increase of carbon uptake by the ocean over time. So the more carbon goes into the atmosphere, the more is taken up by the ocean. What these estimates demonstrated for the first time, that there's actually a lot of variability around. So there can be more uptake than we would have expected, and then cease in uptake, or that the Southern Ocean loses carbon again to the atmosphere, and then a steep increase again. So it's not just the atmospheric CO2, and especially in the Southern Ocean, this variability is high. There are differences in circulation and sea ice and biogeochemistry can create large variability of the carbon sink. And that's why it's really important to get good observations, because we really don't have to know if we don't understand the variability, we don't know if the carbon sink is accelerating, if it's weakening, if there's any change, because we can't separate a significant trend from the variability that we see. So we need these observations to really understand how the variability looks like, and then in the next step, what drives this variability, and can we understand why we have it in the Southern Ocean and where it comes from, which makes the Southern Ocean again a very interesting region to study and to talk about. And what we see at the same time is that models, so the the models that are driven with the observations from the atmosphere in terms of wind and humidity and temperature, which we can see here in green compared to the PCO2 products in blue, don't simulate this change or this strong decadal variability. So here again, we have the variability going, an increase in the carbon sink, then a decrease, and then the strong increase, whereas the models simulate a continuous increase of the carbon sink. And this is one of the big questions: why do models don't simulate it? Why do observation-based products show it? And the question is, are the models wrong? Is the extrapolation of the data wrong? Or maybe even both not right? Or is it a mix of both? So this is one of the big questions that people working or scientists working on the Southern Ocean physical carbon pump in the last years have tried to answer. And I will go into a few aspects to show you what we know by now and how variable the Southern Ocean carbon uptake really is. So the main problem with the observation-based products that I want to focus first is, again, the number of PCO2 measurements that we have in the Southern Hemisphere. This is a similar plot like what I showed you before, but this time it shows in color not the observed partial pressure of CO2, but the number of months that actually have data. So we can see that, as I said before, the North Pacific and North Atlantic, we have a lot of trajectories where we have almost we have almost 48 months, so complete sampling almost of the ocean. And then if we go to the Southern Ocean, we have a few routes coming down here from Tasmania. And we have, I think these are probably French cruises from the Cargèse Islands. And then in the Drake Passage, there's good data coverage. But once we go to other regions, we see we really don't have enough data to get really good estimates of the Southern Ocean carbon sink. And to just illustrate to you how that affects the estimates, we have here again two of these methods that estimated the Southern Ocean carbon sink. And in the last years, we got these bio-Argo floats that I showed you before that are flying around on their own, in addition to ship-based measurements. And there are now 130 active floats that are organized by the SOCOM project in Princeton that are flowing around. And then people did I think this is 2018. For this year, they asked the question, what happens if we add the data from these additional floats compared to if we only use ship-based measurements? And then you can see here in orange, the only ship-based measurements. That's the same that was used for these curves. And then once we add the additional SOCOM data from the floats, the estimate changes to this one. And then if we only use the SOCOM data in the Southern Ocean, the estimate looks like this. So this already shows that these observation-based estimates at the moment are just extremely uncertain, that just adding a few additional measurements or a couple of additional measurements gives us a completely different answer on how strong the carbon uptake in the Southern Ocean actually is. And this shows how important it is that we get more and more of these measurements, and how difficult it will be to go back in time where we didn't have these measurements. So I don't want to say it's just guessing if you go back, but it's the best we can do. But it shows that based on so little observations, even the best extrapolation methods, the best neural network or artificial intelligence schemes, they can't overcome the lag in observations that we have over the past decades, which is frustrating at one time, but on the other hand also I think a good message to move forward, that we need more observations to understand or to quantify the carbon sink in the Southern Ocean, the most important one in the ocean. And just to look how this looks spatially, so we have here the estimated RC CO2 fluxes for summer, for winter and annual. And again, if we only use ship-based observations, if we add the bio-Argo floats, and then if we only use the bio-Argo floats in the Southern Ocean, And we see that even for the annual picture, it gives a very different view of or perspective of how much carbon leaves the ocean, how much gets into the ocean. And the biggest differences are in winter, but there's also differences in summer where we have some observations. Winter, there are almost no observations at all. So just again, these maps to show how uncertain our estimates are by now and how important it is that we get these floaters there, that we get the sail drones and the sailboats in there to get a better handle on how the Southern Ocean carbon sink actually looks like. And so another way to see how these methods work is actually to use models to evaluate their performance. So this is what people did here in a nice study. They used 100 different ensemble members of an ocean model that simulated the Southern Ocean and the Southern Ocean carbon uptake. And what they did is they sampled each model at the places where we have observations. So they basically imagined that this model simulation is the real world. And then so we have, in the real world, we had an observation on May 19th, 2019. So we take this value out and create the data that would have been observed with the same observation coverage as in the real world. And then they used these different pseudo observations and used the same neural network that was based on the real observations and came up then with a reconstructed map of the partial pressure of CO2 and of the RC CO2 flux for each of these different ensemble members of the model. And then you can compare the real flux in the model compared to the reconstructed flux based on the observational coverage. And what they really wanted to look like is how good is it on seasonal timescales, how good is it on decadal timescales, and how good is it on subdecadal timescales. So the full signal that you get, you can detrain it and then decompose it into a seasonal cycle, into decadal variability and subdecadal variability. And now I'm going to show you how that looks like if it's actually done for 100 members. And what you can see here on the left side is the differences in variability due to the sampling between the actual modeled flux and the reconstructed flux based on the sampling. We can see that the seasonal variability is slightly overestimated just due to the sampling, a little bit everywhere, not so much in the northern hemisphere. So this is the northern hemisphere, this is the tropics, and this is the Southern Ocean, or subpolar northern hemisphere. And the subdecadal variability is actually not too bad. It's a little bit underestimated. But the real important result of the study is that if you look at the decadal variability, the reconstructed fluxes based on the models is around 30%. The variability is around 30% higher than the actually simulated flux. So this shows for this one neural network that just the way the neural network uses the observations and the number of observations it has, it creates a far too large decadal variability of the Southern Ocean, a significantly too large one. And this is something the observation, ideally we could train or we could improve the neural networks that this doesn't happen anymore because we can't get more observations. So this is the only way forward, but this is a nice thing to evaluate these methods with the pseudo observational data. So you can actually see what's only due to observations and observation coverage and the extrapolation and what is and how good they are. And yeah, I just put these things here again to show the problem with the coverage and what it creates. And it's quite significant to get a 30% overestimation of the decadal variability. And yeah, maybe something you shouldn't repeat, but people are starting to call this bump in the carbon sink now the Landschützer bump, but it's not very nice to do that because it was a really great result at the beginning. But it just shows how big the question is because it already got a name attached to it. And then what they did as well in the study is to show if we add the additional float measurements and if we would have had them over the entire observational period since 1980, how would the variability actually look like and how good would it be reconstructed? So if we had used bioargo floats, we wouldn't have this overestimation of the Southern Ocean variability. Actually, it would have been a small but not yet significant underestimation, but this is compared to this difference, it's tiny. So this shows that using additional floats is the way forward to reduce this uncertainty and to get a better handle on the variability of the Southern Ocean carbon sink at decadal timescales. So what we know by now is that the observation-based products likely overestimated the decadal variability, and also, but we still don't know if the models underestimated it. And that's where, first I want to talk also about the trend. So there's not just the difference in decadal variability, but there's also, if you look on the reconstruction, on the observation-based estimate, you have a larger trend in the increase of the carbon sink. So this time the carbon sink positive means into the ocean, than in the observations. And here, what they did as well, they did the same thing. They used a model, this model called FISON, and they have the simulated carbon flux, and then they simulated it, they sampled it or used observations exactly at the places where the ships, so the SOCAT observations are, and reconstructed the carbon sink again with the neural network, and they get a larger trend also, not just a difference, but also a larger trend over the last 20 years. And they get the same thing this time when they add the different floats from the SOCOM project. So for the difference in the trend, to get this difference away from, get rid of this difference, we don't only need additional SOCOM floats, we need something more, and we basically need Argo floats in the entire ocean, and then we get a trend that's similar to this one. There's still an offset that the reconstructed fluxes are generally higher than the actually simulated fluxes, and that's just due to the neural network that is used. If you use another one, so this time the Carboscope, you still have the difference in trends, but once you have bioargo floats everywhere in the ocean, the reconstruction is almost perfect. And yeah, it's again just shows uncertainties. It shows that the trend that we get, the higher trend in the observation-based products over the last 20 years is basically entirely due to the way we sample the ocean. So likely there's not just the variability that's overestimated in the PCO2 products, it's also the trends. But and if you want to see where it comes from, it almost entirely comes from the Southern Ocean, from the Southern Ocean. Because this difference that we can see here is the same that we can see here, and also here. So the reconstructed trends are higher, and this is entirely due to the Southern Ocean. And yeah, so that's where the work needs to be done. And I said it sounds very critical what I said about the PCO2 products now, but it has been immense work that has been done, and it's the best we can do at the moment. And so I don't want to say that we shouldn't use them. It's really the best we have, and it's an immense amount of work. But I just wanted to show here what can go wrong and how conscious the community is about it and what they're trying to improve it, and that they're working day and night to get it better. Yeah, and this is the difference in observational coverage over the time here. So in these decades, we have almost nothing in these places, and then if you add it, then you get a different estimate. And if you sample it all the way with the same coverage, you wouldn't get this difference. And yeah, after having said this, I said we are working, or everyone is working day and night to improve this. And one way to do it is that they approach these sailing boats to put the measurement equipment on their sailing boats during the races. in which they did. So we have over 129 days of observations. In addition, 250,000 observations actually in total that came to it. And the question is now, how does the sailboat data actually change the RC/CO2 flux estimate? And there's a really nice paper by Benke all about this, and I'm going to show a few slides from this paper now. And so the sailboat started here in Hamburg, and you can see the measurement equipment, which is actually not a small equipment still. It's really great that the sailors take it with them, because not all do it, so I'm not sure how much it slows them down, but I guess it slows them down a bit. So they're doing a good thing for the environment. And here you can see the sailboat where it was sailing and went down to the Southern Ocean. I'm not sure if it went this way or this way, but I guess just with the current. And so the number of observations there is really low, so adding this one line potentially gives us a better estimate. And the question is, how big of a difference does one line make? And that's the question. What they did now is they used the same neural network without this additional data and with that additional data, and looked how the estimates of the RC/CO2 flux for this year changed. And this is what you can see here. So you have a little bit of numerical noise, because if you add additional data to the entire system, it also changes somewhere else, but it's not significant. And everywhere where you have siblings, you get a significant difference of the ocean carbon sink. And the most important place is here in the Southern Ocean, where just adding a few data points changes the entire flux in this band here by around 0.3, 0.4 more carbon per square meter per year. If you add this data, or if you don't add it. So we have, to give you an order of magnitude how much this is, in total in the Southern Ocean, this reduces the uptake of carbon by around 20% compared to the mean flux. So it's pretty significant. Globally, it doesn't make such a big difference, but for the Southern Ocean, it's a huge game changer just to have one more line of data there. So if you get these lines more and more often on more and more sailboats, in Switzerland we also equipped one sailor now with these measurements, led by a group of Niki Gruber and Thomas Fröhlicher here in Bern, which will give us even better estimates. And as this data also goes into the training of the neural network, we get a significant differences at the other places, until you can just see how much of a difference that makes in terms of longitude and latitude. And we see the biggest difference here, and the different years as well, because of the different training of the neural networks. So there's a large effort that's being made now for really improving these estimates and for getting a really better handle of what is going on. And I think in a couple of years we will have a much better idea if we get more and more of these observations. So it's a pretty positive message now from here, I think. It wasn't that good in the past, but it's going to be much better in the next years. So I talked a lot about PCO2 products, but we have a different method as well to estimate the RC/CO2 flux in the Southern Ocean. And that method is global ocean biogeochemical models that are used at higher and higher resolution to simulate the ocean physics and the ocean biogeochemistry and the carbon cycle with it. And I want to show you what these models can do, and also what they can't do, what their weaknesses are, what their strengths are. And let's directly dive into this. So first, the comparison to the products that I showed you before. So here you see the flux into the Southern Ocean again. So this is negative, means into the ocean. And for the different regions, for the ice-covered regions, subpolar and subtropical regions. And what we see in general is that there's a much bigger uncertainty for the models. So with some models that are here, some that are there, and the standard deviation is quite high. And the uncertainty comes a bit from all regions, whereas the main flux comes mainly from the subtropical region. And this becomes also obvious if you look at these. I guess it's probably hard for you to see, but the green lines are the more scattered around, whereas the observation-based products agree more or less, probably because they're based on the same observations, and all the different models have different kinds of numerical equations behind them. And also then if you look at the time series of the mean flux, again we have the models and the observation-based methods, and then a couple of other methods that I don't want to talk about here. We see the wide range of different mean fluxes of the ocean biology chemical models, so there's a large uncertainty there. And the question is, where does the uncertainty actually come from, and why do these models differ, and what can we learn from it, and what can't we learn from it? Because looking at this, it almost looks like they're saying as a model they're fairly useless if the uncertainty is that high. I want to convince you that they're not that useless as they look like. So here, this is a paper that I worked on as well the last years, and it's we separated in the models. What we can do is we can use different simulations where the atmospheric carbon increases but the climate stays constant, or the climate changes and the CO2 in the atmosphere remains constant. So we can separate the total flux here in green, the uncertainties that I've shown you before as the different lines, into its different components. So we have the one component here in red, which is the anthropogenic increase in carbon, which is the flux due to the anthropogenic increase in the atmosphere in a stable climate. And then we have in orange, the flux with increasing carbon in the atmosphere, and the effect that comes in addition with the additional changes in climate. So if the ocean warms, then there's going to be less uptake of the wind changes. There might be more ventilation and more uptake, and this flux is fairly small. And then we have the natural, maybe we start here with the brown one, this one here, with the huge uncertainties. This is the natural pre-industrial state of the Southern Ocean. How much carbon does it lose? How much does it take up in an equilibrium state? But it's, as the models are not all in equilibrium, there's also a flux that I'm going to talk more about due to the drift of the model. So it might not just be the natural flux, but the total global ocean might just lose carbon in a model until it's in equilibrium with its own equilibrated condition. And we also have a flux that is due to the influx of carbon from rivers and the burial of carbon. So at the moment, what we think that, based on observations, is that there's more, in pre-industrial times, there was more carbon coming in from rivers that was buried in the sediments of the ocean. So the ocean was constantly losing carbon to the atmosphere in equilibrium. And so there was already a flux out of the ocean. And there the uncertainties in the models are very high because they use different ways of how they prescribe the rivers and have different ways how they simulate the burial. So we have a large uncertainty from this flux component. And then we have also the difference in the natural carbon due to climate change. So if the ocean warms, the carbon that's already in the atmosphere and the ocean is going to be lost to the atmosphere, which is this line here. And the first thing that I want you to get from this graph is that the big difference in the models mostly comes from this brown thing here. So the natural state of the ocean, carbon flux in the Southern Ocean, which is due to differences in circulation, but also due to difference in biology and biogeochemistry. And that actually the increase in, or the change in this carbon, in the carbon uptake on the carbon CO2 flux in the Southern Ocean is fairly well constrained by all the models. So they simulate this almost the same change, the same uptake of anthropogenic carbon, but they differ a lot in the present days, in the pre-industrial state and in the natural carbon cycling. So if you're only interested in how much more the carbon takes up from the atmosphere, the models are actually agreeing quite well among each other. But if you want the total flux at present day, then we have this large uncertainty. And I said that a large part of this is due to the spin-up of the simulations and the models being in equilibrium. And here you see that part of the flux, which is due to the drift. And we see that models that are spun up only a couple of years have a larger drift flux, and ones that have been run for a long time before the actual simulation starts, they have a generally smaller flux. The reason for this is that the models are usually initialized with observations. So we put in the temperatures in the deep ocean and the salinity that we have right now. But each model has a different equilibrium in itself. So then it runs and it loses heat, or it takes up heat, it loses carbon, or takes up carbon, until it reaches its own equilibrium state where the model is in equilibrium with the atmosphere. And it takes a lot of time to do that, to get all the deep waters coming back to the surface, where the circulation times are up to 2,000 years. So if we don't do this spin-up, we won't get, or it's very unlikely that we get a model that is in good equilibrium with the atmosphere. So we have a large difference in the natural flux just because of this drift. And then in addition, what I said is that we have the difference between the land-sea river carbon flux and the burial and sediments. And just here you can see what fluxes are prescribed in these different models. It's a petagram of carbon per year from rivers to the ocean. So we have this mean flux with an uncertainty that's larger than the mean itself. And this is what the models simulate in terms of burial. So there's just this large uncertainty in terms of how much carbon goes in from the rivers, how much goes into the sediments, and how much is lost to the atmosphere. So that we get this difference flux between both in the models that is 0.03, so a small uptake in this case with extremely large uncertainties. And just to give you an idea how that looks like, how observation-based estimate of this number looks like, it's around 0.66 petagrams. So we think that the ocean in pre-industrial times has lost 0.6 petagrams, but the models can't simulate this. And they simulate it in very different ways. So this is why the natural flux in the models is so different. We have such a different drift flux, and we also have such a different way in simulating rivers and burial. So what I want you to take away from this is that the models are not too bad in simulating the change in the carbon flux in the Southern Ocean, but they're not very good in simulating the natural state of the Southern Ocean, and thus not very good in simulating the total flux. So every method has its strengths and weaknesses. And why do I talk about the Southern Ocean? It's because we think that these differences in the spin-up mainly are happening in the Southern Ocean because they are the old waters that are coming up. And just, it's very difficult in models to pin that down where it comes from, but we can do is to plot the regional air CO2 flux in pre-industrial times in the models compared to the global air CO2 flux. And we get a almost linear, almost one-to-one relationship in the Southern Ocean, and we get no relationships in the other basins, which basically means that the global flux, CO2 flux in the models where they're not in equilibrium because they are losing or taking up carbon, it's almost all happening in the Southern Ocean, and it's almost all there where it's happening. So these drifts, they don't really affect the other ocean basins, but they really do affect the Southern Ocean because of its unique geography with all the upwelling waters in that region. And that makes, again, this region just not only because of scarce observations, but also because of its geographical position and upwelling of very deep waters, makes it also complicated to simulate. So it's complicated on both ends of our spectrum to estimate the carbon flux. And just to go into another issue with why there are still differences in the anthropogenic carbon uptake is, if you look at here the increase in CO2 concentration over the past 250 years. So here we have higher variability because we have actual observations. These are reconstructed from ice cores, so this variability would be here as well. And we see that most models actually start in 1850 because it's computationally less expensive, because the time to simulate is shorter. But we see that we already had an increase in carbon since before 1850. So if you spin up a model with the conditions 1850 where you start, you put in 10 ppm parts per million of carbon, or you put in more carbon into the ocean because the atmosphere is already higher, and you spin it up 1,000 years, so all this higher atmospheric CO2 goes already into the ocean. Whereas when you spin it up with the CO2 from 1760, when it was lower, the entire DIC in the ocean, so dissolved inorganic carbon in the ocean, will be much lower. So just by using a too high PCO2 at the beginning of your simulation, during the spin-up of your simulations, you have a too high carbon content in the ocean. And then when you increase the change in that carbon content, then the ocean won't take up as much carbon because it already has too much inside in the deep waters. And if you look at how that looks like, so we did two simulations, one where we spun up the ocean 1850 with 1850 conditions and one with 7065 conditions. We see again that in the global ocean there's not much difference between the two simulations, but if we go to the Southern Ocean, we have a much higher uptake here in these regions in the simulation where we spun up the ocean in 1765. And this is again because the old waters are coming up there, and the old waters are then too high in carbon already in the simulations that started in 1850. So the uptake there is too small. So these are all different kinds of strategies, so that by saving computational costs and starting in 1850, we don't change the estimate of the carbon sink much in the global ocean, but we do change it in the Southern Ocean. And the difference decreases with time here. So this is for 3 different calibrations of the model with weak and strong and medium mixing. But they almost all show the same thing. And the differences become smaller by 2020 because the increase in the atmosphere has been so high that the difference compared to the 10 ppm is small, but it's still there. So this is also why our estimates in the Southern Ocean are very difficult to make at the moment with models. So ideally they would all start before 1850, but yeah, and then model centers need to redo the spin up, and that costs a lot of money as well in terms of computational costs. And then there are ways, but that are then we can see as well that physical dynamics play a role. So here we see the air CO2 flux, the change in air CO2 flux, or the anthropogenic uptake in different models. And there's an explanation for the differences. That interfrontal sea surface salinity, so the salinity between the polar and the subtropical front plays a big role, but I just wanted to show this here as a small teaser. I will speak more about this tomorrow. We see that physics drive the differences in the CO2 flux already, but just wanted to bring it up quickly here. I could stop here and a break for tomorrow. I don't know, JB, what you think about time? Because I want to go now to the interior.
Tell you, but that's about an hour now. So you can stop here or continue it, but as you wish.
No, we can do. I think it's a good time to stop.
Okay.
I probably talked too much already. Anyway.
No, I don't think so. But yeah, so let's. Any questions for Jens?
Hello? Hi. Can you hear that?
Yeah, I
okay?
can hear you, yeah.
All right, thank you for that talk. This is coming from a biogeochemical person, so it's not my field. But, so you've touched on a lot of them, but to summarize, what would you say are the active open research questions that you see this field going into that people are working on?
Yeah, thank you for the question. That's so maybe I start with the part I'm more working on, so on the models. So I think the most important part is to get the better estimate of the carbon that comes in from the rivers and that goes out through the sediments to get something in the models that resembles the real world in that sense there. So that at the moment we are good in terms of the anthropogenic carbon uptake, but we are not good in terms of natural and total fluxes. And I think if we want to use the models for these fluxes as well, we need to get that right. And then the other part is, I think, to see the impact of a higher spin-up. there still remains the question, because if you run a longer spin-up, your model will be further away from the real world conditions. So to get a handle on how big that problem is in that sense. And so I think that would be the main parts in terms of what we would do for the models. And for the observation-based products, I think we need more observations, and then once we have them, I think they might even be helpful to extrapolate, to then make better extrapolations of the past data that we have, and maybe try. I don't know if that's possible, because I'm not much of an observational person. If you can then improve the extrapolation methods to even use the past observations in a better way, to get a better idea of that. But and then a big effort is now even to keep up the measurements that we have, because there's less and less funding available. And in the North Atlantic, we see a decrease in observations already. So I think there's a lot of public, not just research work, but also funding, or promote funding actually, which is important.
Thank you. Any other questions? Maddie again.
It's the same person again, sorry. What physical processes specifically do you think are the most important for determining the ocean's uptake of anthropogenic carbon, and how are those processes changing?
Okay, I think the most important is the upwelling of circumpolar deep water, and then the formation of mold and intermediate water masses once they move northward in the Southern Ocean. And the big question, I think, is how they are going to change in terms of climate change. What I'm going to talk more about tomorrow is what happens if the sea ice disappears, if the Southern Ocean becomes fresher, especially then can it become that fresh that we have much less formation of more intermediate waters, and so how's all that going to affect the way the Southern Ocean circulation and then the carbon sink works as well? And one thing that I forgot to say about the models, I think, is something that that has been shown to be important as well, as that we don't have so far melting ice from Antarctica and there, so there could be an additional freshening, or there will likely be an additional freshening from the glaciers on Antarctica that's not prescribed in the model simulations, and potentially moving icebergs as well, that are not in our models. And if the icebergs move further north and then melt further north, they could also affect the density of the surface ocean and then the circulation.
Thanks. Yep.
Hi, thank you for your talk. I have a question about the figure you showed about the different models having different mixing. And I was wondering if you can tell us more about that figure, and specifically like how this mixing is maybe parameterized in these models. Yeah, that one. Thank you.
It's so the model that we used here is a model of an Earth system model of intermediate complexity. What you can kind of see on the plot here on the left side, it has, I don't want to say something wrong, but I think it has around 40 times 50 grid cells. So it's not similar to the models that I showed you before. It's very intermediate complexity, but the advantage is that we can run it without having high cost. So it was the first test. We are probably going to repeat this now with a higher complexity model. But the disadvantage of using a model that has intermediate complexity is that there's a lot of parameterization. So we have just a parameter for diffuse mixing, and there that we can, there's circulation as well, advective motion that we didn't change, but this is diffusive mixing, and that we can increase and decrease to get more or less realistic conditions. And this was just a test to how sensitive this difference in the flux in the Southern Ocean is due to this parameter, to make sure that we just didn't find a result that we get if we have very high or very low diffusive mixing. So it was more to show that that these estimates really are robust in terms of that the Southern Ocean will be different if the models are started earlier and spun up with lower PCO2 in the atmosphere, or with actual pre-industrial PCO2.
Okay, thank you. I have a following up question about this graph. So why does the difference among the different mixing schemes improve with time?
Okay, yeah, that's a good question. Yeah, thank you. It's basically the one simulation that starts in 1850 sees no difference. So once you have the atmospheric carbon starts to increase in 1850, the uptake of carbon by the ocean will be very tiny, because in 1851 it's just 0.2 ppm more in the atmosphere compared to the spin up, and then by 2020 it will be 100. I don't know about how far we are at the moment. 422. It will be 140 or something. Whereas the simulation that started in 1765 has in 1850 already a ppm of difference of 10 ppm. So then in 1851, for example, you would have a difference of 10.2 compared to the other simulations of 0.2. So there you get a really big difference in terms of how much more carbon is in the atmosphere compared to the spin-up. But once you get to 2020, the relative difference becomes smaller, because one is at 140 and the other one is at 150 ppm. So then it's just a difference of a couple of percentages. But at the beginning, because one just starts in 1850 and it just has a small difference compared to its spin-up at the time. And then it just decreases with time, because atmospheric CO2 increases that high that a difference of 10 ppm isn't that much anymore in relative terms. I hope that made sense.
Yeah, so does this mean that in the future we don't have to worry about the mixing scheme?
I think we have to worry about the mixing scheme, but we have to worry less and less about if we start model simulations in 1850 or in 1765. So the mixing scheme was just a sensitivity test. So it's more about worrying when the model starts. So if you want to know the carbon flux in 2100 in a high emission scenario where we are at 1000 ppm or something, then it doesn't matter if we started at 270 or 280 ppm. But now when we are already only at 420, and then it still makes a difference. But yeah, in the future, it's unlikely to make a difference if atmospheric CO2 continues to increase exponentially.
There is many other reasons why we should care about mixing. One last question before we move on.
Thank you for the talk. It was great. Appreciate it. I had a quick question about the bioargo measurement variability ranges that you presented in that one slide. Do you think this is mostly due to, and I don't have a carbon background, do you think this is mostly due to temporal or spatial biasing, or is there something fundamentally different about the way the measurement is being made?
I think it's mostly due to the amount of sampling. So if you sample, that's basically, maybe I put up the, which one shows it? If you sample, like here, if you sample the ocean, so as if you had biogeochemical argo floats almost everywhere, then you get so almost everywhere they're still separated. I don't know how many. I think they put 300 in the global ocean, but in this test, then the differences disappear. So I think it's mainly due to the amount of observations and not on the kind of observations. But the ship-based observations obviously have a much smaller uncertainty than the observations an autonomous floater has, where they can't be monitored or repaired during the time. So there might be a drift in the sensors, or you don't know how well the sensor works. So the uncertainty is higher, but the differences here in the reconstruction, I think, just come from the spatial and temporal variability and not the different kind of observations.
Thank you very much.
Thank you again, Jens. So we'll move on to Alessandro's lecture. morning, Al. So, yeah, I don't have much of an intro, so we'll move to this lecture from Alessandro, who will focus on BGC, basically, and production.
So can you see everything, JB?
Yes, we can, and yes, we can. And Al, so the floor is yours.
Okay, thanks, JB. I hope everyone can hear me in the room. Thanks, Jens, for the presentation before. That was really very interesting. I'm very sorry I can't be there with you today. Unfortunately, I had an argument with a metal motor vehicle as a pedestrian a week or so ago, and so I came off worse in this altercation. And I'm hence back in my kind of spare room, reliving the glory days of the COVID pandemic, speaking into a computer. So hopefully this won't be a good replacement for an in-person lecture, but hopefully it won't be too bad experience for all of us. Yes, as JB said, I'm going to talk about ocean biogeochemistry and primary production. But like Jens, I want to start a little bit by telling you my kind of background, how I got to this position. So I'm trained as a biologist. I did an undergraduate degree in marine biology in the lovely city of Newcastle upon Tyne in the northeast of the UK. I graduated in 1999, a long time ago, it seems now to me. And then I went on, I spent quite a lot of time actually trying to find the right PhD project when I started my career. During my degree, I got very interested in the Southern Ocean and the role of iron in regulating productivity in the system. And, really what I wanted to do was learn how to use these ocean models that Jens was mentioning in his presentation to try and test hypotheses and understand the importance of different mechanisms. And I had a lot of trouble trying to find a PhD where I could do that, largely because in the UK, as is common in most European countries, PhD is quite short. It's 3 years, maybe 4 years maximum. And that's quite a short period to learn new skills and then also use those new skills to go on and, make some new scientific discoveries that you need for your PhD thesis. So I went to do my PhD in the US, actually. I took a kind of random walk to Stanford University in California to work with someone called Kevin Arrigo, that some of you might know. And I worked on ocean biogeochemistry of the Ross Sea. And this was a longer PhD. It took about 5 and a bit years for me to graduate, but it meant that I was able to really pick up these new skills and take the time to expand my portfolio of interests as well. And so I graduated there in 2006. And then at that point, I moved to Paris to work with Laurent Bopp at the LSE, same place where Jens was. And I spent around 4.5 years in Paris, really working on global models, trying to understand the link between ocean carbon cycle, ocean productivity, and changing nutrient dynamics. And this was a really productive, fertile time. It was really exciting and enjoyable. Following that, I went down to a different hemisphere, so moving a bit further on the map, and I spent just over 2 years in Cape Town in South Africa, working with Pedro Monteiro, Seb Swart, who I guess isn't there anymore. He was there last week, I think, with you. Seb and I used to share an office many years ago, and this was a great opportunity to kind of work on modeling, but also work more on developing infrastructure, observational infrastructure, to measure iron and these kind of things in South Africa. And then I moved to Liverpool, where I took a permanent position in 2012, and I've been there since, and I was made full professor in 2018. And my kind of USP is that I use models. That's my kind of main skill set, but I'm a biologist at heart. I'm not a mathematician or a physicist, so that's not really my deep expertise. And so I really tried to position myself really at the sort of link between modeling and observational science, and trying to work across those two domains to really operate, I like to think, on some interesting questions and some interesting problems. As part of that, I've gone to sea quite regularly over my career. The picture you can see on the top left, I'm on the left, kind of looks like I'm in a kind of witness protection scheme. That's Baptiste was there with me. That's where he and I met many years ago on the Aurora Australis, running a section from Hobart down to Antarctica. JB, I noticed that there's a new IPY in 2032-3, so we should try and go on a cruise together again, just to sort of mark this kind of decadal scale interaction we have at sea.
That would be lovely,
and
Al.
the picture on the right
Whenever.
is my most recent time I was in Antarctica. This was on the Tara, where I was chief scientist on this sailboat that goes around trying to collect large amount of genomic information. And, you know, doing this is like really fruitful. It's a really exciting part of my work, and it's really where a lot of the new ideas are generated, really, from going to sea, observing the ocean, interacting with colleagues in this environment. And I think it's a really important part of the career of being an oceanographer if you're interested and able to do so. I've also worked a lot in recent years with the IPCC, so I was one of the lead authors of the Special Report on Ocean and Cryosphere in a Changing Climate, this ESROC report that contributed to the AR6, and that was very interesting. And one of the most interesting aspects was that I was one of the authors of the Summary for Policymakers, so I had to go to this in-person kind of approval session with all the governments in Monaco. When was that? Just before the pandemic, right? 2019, that would have been. And the figure, you can see a picture there on the bottom left of us on the stage. That's myself. You know, you can recognize your favorite oceanographers, Mike Meredith, Thomas Frelicker, Bob Halberg. You know, in a huddle, trying to figure out how we are going to respond to some criticism of some sentence we have written in the Summary for Policymakers from a particularly interested government or set of governments. And that was a really interesting part of my kind of career progression, because it really made me realize about what really do policymakers care about in terms of the science we do. How can we articulate the science we do in a way that makes them interested in what we're doing, and interested, importantly, of course, to take action on the findings that we have. Okay, so hopefully that gives you a little flavor of myself, my background, what I do. So today I'm going to talk about productivity and biogeochemistry, and I'm going to, you know, these lectures, I've designed them very much as kind of two parts. And so today we're going to try and set the scene. I think there's a lot of physical oceanographers there giving you lectures, I think. So we're going to change pace a little bit and start talking about the living organisms in the ocean and what they're doing. And one particular thing is the importance of this flux of carbon linked to the net primary production. We're going to talk about some of the key governing processes, and I'm going to end by telling you what we think, what our best estimates are for how productivity is going to change in the future with climate change, with a focus on the Southern Ocean. Okay, I would say interrupt me. Normally, I think that would be fantastic, but I think it's pretty clunky on Zoom, so maybe it's best if we just do the same as Jens did, and we can just have a Q&A at the end, and if needed, I can pull up any relevant slides. Okay, so let's get started. So this is one of these, like, you know, lovely diagrams that we see all the time about the role of biology in the ocean carbon cycle. Tons of arrows, lots of kind of artistic interpretation being used to the maximum. You know, we've got fish, we've got the land-ocean continuum, you know, some particles, bacteria, even like breaking down bacteria into different forms, so the archaea as well. And, you know, this is very complicated. There's lots of processes going on. And so at the risk of not patronizing you, I'm going to show a slide that I showed for my undergraduate, the final year undergrad lectures here in Liverpool, which is where I just sort of simplify this figure into a very simple view about what's going on with the ocean carbon cycle, where you can see I've really extended my artistic limits in terms of my attempts to represent some of the key processes. But really what we're thinking about is the fact that there's some, you know, physical chemical processes that set an equilibrium between CO2 in the atmosphere and CO2 in the ocean. The biology intervene here. You can use your own interpretation of what I'm trying to represent. But there's a whole lot of ecosystem processing, and then there's a sinking flux of carbon that regenerates in the ocean with similar physicochemical processes going on, some linked to biological activity like fragmentation of particles by zooplankton, trying to garden, you know, curate a kind of mesopelagic garden. And ultimately, the physics brings this all back to the surface. But within this, there's a key flux, and it's represented by this kind of arrow here, and it's called net prime production. And that's the one we're going to focus on, because without this arrow here, we don't care about the whole rest of the diagram, right? We'd be in an abiotic world, and physics and chemistry would rule. We would be able to use, you know, physical laws and chemical laws, and we wouldn't have to worry about all the mess of the biological processes. But we don't, so we have to, okay? And so that's what we're going to worry about today. Before we get started, you know, again, at risk of not patronizing everybody, but it's good to call an apple, and so we know what we're talking about. So there's some definitions we need to use here. So the first one is gross prime production. Okay, so this is the photosynthetic reaction, for those who don't recognize it. It's the combination of CO2, water to produce a sugar and oxygen, okay? So hopefully everyone knows that, or at least has come across it at some point in their career to date. What we're going to talk about today is what's called net prime production. And so that's this rate of photosynthesis, and we're going to subtract off the respiration. So some of these sugars are broken down by the photosynthesizer to fuel their cellular metabolism in the mitochondria. And so the balance between the two we call net prime production. In some places you might hear about net community production, which is this net prime production minus all the respiration by the entire phytoplankton community, by the entire ecosystem community. That might quite closely approximate export production, if you know about that. But we're going to focus here on NPP, okay? This is a critical process whereby, you know, we might argue it's the most important biological reaction in the ocean, maybe the most important reaction. I don't know, if I were there in person, we could have a discussion about that over a beer or have an arm wrestle. But, you know, using the energy in the sun, inorganic molecules are converted into organic molecules, and, you know, that's a really critical process. So what does it look like? It's we have a system we have an assay to measure primary production in the ocean, but it's not used in a very widespread sense, and we tend to rely on satellites to give us a measurement. So we exploit the fact that this absorption of light during the photosynthetic process alters the optical properties of light. Satellites can pick this up, and then some mathematics can be done, and that alteration to the optical signature of the surface of the ocean can be used to infer an abundance of chlorophyll, for instance, that you might have heard of, or the amount of productivity that is occurring. And so we see, you know, high productivity in upwelling zones, high productivity along the coasts. If we look at the Southern Ocean, you know, it's beautiful to see down at the bottom here. Relatively low productivity offshore, high productivity near the coast again. So again, I think, you know, you really need to worry about this process. It's a really important process. It catalyzes almost all of the responses, all of the contribution the ocean makes to ecosystem services. If you're worried about ecosystem diversity, biodiversity, if you're worried about feeding people with protein from the sea, if you're worried about water quality and whether you have a harmful algal bloom or not, this process is at the nub of the matter. I totally agree with Jens. You know, the contribution of the biological pump to the ocean carbon cycle is not massive. And I certainly agree with his assertion at the start of his lecture. But nevertheless, all of the biological contribution, however large it may be, is catalyzed by net prime production, as I showed at the start. There was no net prime production, there'd be no contribution. And then, yeah, finally, it's an input for upper trophic levels. So if we want to forecast somehow the response of some member of the more charismatic community of the ocean, then we need to know this. This is the energy and organic carbon input to the base of the food chain. So again, at risk of not patronizing you, I'll go very quickly, but if you've never heard of this, photosynthesis is split into two reactions. They both occur within the chloroplast. This is a very simplified representation of that. The first are a set of reactions known as the light reactions because they need light. Okay, those occur in the thylakoid. There's a stack of thylakoids here. The important thing is that these produce two things. They produce ATP, adenosine triphosphate, energy, and NADPH, which is what we call reductant. So this is the energetic and chemical input into to drive a set of chemical reactions. These occur in a process known as the Calvin cycle. And we sometimes call these the dark reactions. It doesn't mean that they happen in the dark. It just means that they do not need light. Okay, so phytoplankton are still doing this in the light. It's just that they don't need light for this. And the Calvin cycle effectively uses the fruits of the light reactions, adenosine triphosphate, NADPH, to fix CO2 into sugars. Okay, the water splitting reaction that produces oxygen is in the light reactions. Okay, and if you want to see what it really looks like, this is an electron, microscopic view of a chloroplast. And if you see these little kind of stacks here that look a little bit like kind of sort of burgers or pizzas lined up, they're the thylakoids. That's where this is all happening. That's where all this action is going on. So if you want to understand net primary production, we need to think about what is it, first of all? So it's a rate. So it's some quantity of carbon, milligram per square meter here. It could be moles. You could choose per liter, per cubic meter, whatever. There's some amount of carbon per day, okay? And it's generally the product of some rate of growth or some specific rate of carbon fixation. In this case, this would be in units of per day, and the biomass, standing stock. How many phytoplankton do you have? If we have one phytoplankton fixing carbon really fast, versus 1 million phytoplankton fixing carbon very slowly, it's highly likely the million will actually fix more carbon in total. So we need to think about the standing stock of the community. Okay, the first part is the growth rate. Okay, and this is the kind of simple diagram of what a growth rate looks like. If you grow a phytoplankton in the cell, in the lab, or if you monitor their growth kind of at sea in some hypothetical situation, you would see this exponential growth curve of the cellular abundance or cellular carbon changing as a function of time. Okay, and this rate of change in the concentration of the phytoplankton is driven by their standing stock and their growth rate. Okay, and we can write this exponential out as an exponential equation. We can use the natural logarithm to linearize the equation, and then from that, the slope of the line is the growth rate. Okay, so that's how we experimentally go about measuring the rate of growth. If you swap abundance here for amount of phytoplankton carbon, you'd be then approximating the specific rate of net primary production, okay, because there'd be some autotrophic respiration. Many years ago, someone called Dick Epley, who passed away recently, collected a lot of data on growth rate. So that's what you're seeing here, growth rate, in this kind of old-fashioned unit of doublings per day, but it doesn't really matter. Bigger number, bigger growth. And he plotted these as a function of temperature. And what we can see there's this upper limit set by temperature, this exponential relationship, which we call now a kind of Epley curve, which is linked to the role of temperature in driving cellular metabolism, worked on by Arrhenius many years ago. And then what we see is the data. So it's interesting that the data, none of the data passes the line, but most of the data actually falls below the line. So most phytoplankton don't actually achieve these theoretical temperature-constrained growth, and that's because of nutrient limitation, okay? That's because their ability to divide, their ability to build new cells is limited by the raw materials they need to build those cells, okay? If we want to move house, we need, and build a complete duplicate of our house, we need all the stuff that goes in the house, okay? And the phytoplankton are in the same boat. So they require nutrients for kind of two reasons. One is because they're structural, right? They make up the fabric of their cell. So a good example here might be the photosynthetic pigments that are made of nitrogen, or the phospholipid bilayer that forms the cell wall of a plant cell is made of phosphorus. Otherwise, they need nutrients to catalyze cellular reactions. Okay, so RNA, so translation of DNA, RNA to undergo replication is full of phosphorus, right? So you need a lot of phosphorus for this process. And the photosynthetic reaction that we spoke about just now, there's iron throughout that, so you need a lot of iron. And then it's the absence of these key nutrients will either limit your growth because you can't build new cells, or because you can't produce your metabolism effectively doesn't operate any longer. Okay, and if we want to look at nutrient limitation, again, this is a classic result from Dick Dugdale back in the late 60s, where he looked at the amount of phosphorus you would add to a cell culture and the oxygen evolution, right, as a measure of photosynthesis. And you see this kind of nonlinear response that looks very much like Michaelis-Menten enzyme kinetics. And you can describe this mathematically by some kind of maximum rate of enzyme activity, or in this case, photosynthetic activity, some half saturation constant, concentration where you're at half of your maximum rate, and then you can very clearly link the rate of a process to substrate availability. So those models that Jens was talking about in his presentation, these are the kind of equations they're using to drive their model architecture. These, it's not just an equation, it represents real processes, right? When cells want to take up nutrients, so if we're a cell over here and we want to get nutrients into our cellular, intracellular space to put them to work, we've got two processes, that cellular transport occurs in the cell boundary layer. So we're limited on the one hand by the molecular diffusion of properties, solutes, into the phycosphere, the cell boundary layer, and then the ability of our transporters to internalize the nutrient in question from being in the phycosphere to actually being in the cell. And that's what explains this kind of non-linear curve, that you have an initial part which is diffusion limited, which is relatively linear, and then at some point your diffusion is high enough that you're diffusing enough nutrients to your cell boundary layer that your nutrient uptake is then limited by the amount of transporters that you have. So these mathematical abstractions are trying to represent real processes. So what nutrients should we worry about? Okay, and to do this, we can use a concept known as nutrient deficiency. So this is a very influential plot produced by Mark Moore in 2013, so just about 10 years ago. And what Mark did here is that he compared two quantities. He first normalized all the availability of all nutrients in seawater to the availability of carbon. Okay, so for a biologist, we put carbon as our kind of core currency. So he looked at how much nutrient there is, how much there is relative to the amount of carbon, and then he did the same for the phytoplankton's cellular contents. Okay, so we looked at basically how much of a given nutrient is in the cell per unit carbon. Okay, and obviously carbon sits on this one-to-one position, and we use that as a reference point to look at the availability of other nutrients in seawater. Okay, so these are all bioessential. Phytoplankton need these. The black line represents the one-to-one ratio. So anything up in this quadrant, you would say there's way more of it in the ocean than the phytoplankton will ever need. Okay, so even if they grew for an infinite amount of time, they would never deplete the amount of those nutrients. Okay, good examples here are the salts in seawater. So magnesium, for instance, if you like chlorophyll, the center of chlorophyll is made of magnesium. But there's way more magnesium in the ocean than phytoplankton will ever need. Magnesium will never become limiting. Same for sulfur, potassium, strontium, molybdenum. And it's only when we get into this area below the line that we start to get nutrients that are less abundant in seawater than they are in the phytoplankton cells. Okay, and those are called deficient. Okay, so a deficient nutrient isn't limiting. It has the potential to become limiting. Okay, if there's enough phytoplankton growth. And so we can see nitrogen and phosphorus, kind of as expected. Below the line, silicon also for diatoms. And then we have a whole load of transition metals here down in the bottom corner that are at very low abundance in seawater, orders of magnitude more scarce in the ocean, and orders of magnitude less essential in the cell. But nevertheless, there's not enough of them in the seawater to support infinite levels of phytoplankton growth. So they have iron, manganese, cobalt, that's cadmium, copper, and zinc. And nickel is kind of hovering. Okay, so this bar represents the major uncertainty, is the fact that for many of these elements, the phytoplankton requirements can be quite plastic. Okay, so if we want to worry about nutrient limitation, it's in this quadrant that we want to be. We're not going to spend much time worrying about the strontium availability. And the eagle-eyed amongst you, I mean, hopefully you have this on a big screen and not JB's laptop, is the red colors here represents elements that have residence time on orders of thousands or tens of thousands of years. Okay, so they're very abundant in the ocean stockpiles, and they make up the salts of the sea. And it's those elements that have shorter residence times that eventually emerge as becoming limiting in the ocean. Okay, so what does nutrient limitation look like in the ocean? This is a paper that came out last year by Tom Browning, Guillemard, and Mark Moore in Southampton. And what they've done here is they've compiled all the experimental determinations of nutrient limitation that exist in the ocean. Okay, so everywhere where you see a circle on this map, somebody has stopped a ship, They've collected seawater from the ocean, and they've conducted what's known as a bioassay experiment. And there's a sort of graph, there's an example kind of experiment here, and I'll show you some more easy to interpret ones on the next slide. But effectively what the scientists do is they add different nutrients alone and in combination with one another. And then we measure some component of the system, here chlorophyll, right, taken as a proxy for the phytoplankton biomass. And we see which nutrient did we have to add to get the biggest response in terms of chlorophyll. And then you color the circle depending on what that nutrient was. And those colors are all here. And in general, we see this high-low latitude distinction. Okay, so the low latitudes, let's say the Atlantic for an example, most of the low latitude Atlantic is blue, okay, and so you had to add nitrogen to drive a response in the community. And the Southern Ocean, which is what we're all interested in, that's why we're here at this summer school, you can see it's virtually exclusively red, okay, and that means iron. Only when iron was added did you see any response in the phytoplankton community. The backdrop represents two things, okay? So the colored shading, so the greens here, that represents the surface nitrate from World Ocean Atlas. So we see, obviously, the high nutrient conditions to the Southern Ocean because of the upwelling, as Jens mentioned. Then you have North Atlantic, North Pacific, Equatorial Pacific, also relatively high nitrogen systems. And then the blues represent where the nitrate concentration is very low. And then the shading, this kind of reddish color, is an interpretation from a model of the aerosol deposition of iron, so the input of iron from the atmosphere. And so you see it's basically when you don't have iron, or you do have loss of nitrogen or vice versa, that's when these nutrient limitation patterns emerge. Okay, you may have so this shows a kind of like complex interpretation of the circle with some serial and co-limiting behavior, and you can see some of this behavior in the Southern Ocean. There's a split circle there, there's a kind of halo here around this one in purple. In the Benguela we see a lot of this behavior. In the West Pacific and near South China Sea we also see a lot of this kind of split behavior, and I want to just mention that briefly for you and also show you a little bit of what these experimental results look like. Okay, so this isn't the Southern Ocean, apologies for that. This is the Benguela upwelling system. It's a paper we worked on with Tom a few years ago. And I just want to show you the results of 3 of these experiments so that when you may never use these again, but at least when you hear about them, you'll understand where they come from, okay? And so experiment 3, let's find it on the map. It's here, right, near the coast of, I think we're up near Angola there. And this shows you the result of this experiment. So Tom conducted a multifactorial experiment adding iron, cobalt, nitrogen, and vitamin B12. And C is the control. And what we see is in this experiment, it was only when nitrogen was added that we saw a statistically significant increase in the amount of chlorophyll. And then when we added nitrogen and cobalt, nitrogen and iron and cobalt, nitrogen, iron and vitamin B12, we could never statistically increase the chlorophyll above this level. Okay, so in this scenario, it would be singly limited by nitrogen. It's only nitrogen that we need to worry about. The circle is blue. And then we have what's called singular and serial limitation. Okay, so this is experiment 6. This is just off the upwelling here. And in this example, we see again, nothing really happens until you add nitrogen and cobalt, nothing happens. But then when you add nitrogen and iron, you get a massive increase in productivity. So we call this serial limitation. This is when, yes, there is something singly limiting the system, but when you add enough of that, something else quickly becomes secondarily limiting or serially limiting, okay, so in series. And then the final is what we would call co-limitation, okay, so in this situation, we had cobalt, nothing happens, iron, nothing happens statistically, iron and cobalt, nothing happens, nitrogen, nothing happens either. So this is unusual. When we've added either iron or nitrogen, nothing's actually stimulated this community. It was only when we added iron and nitrogen in combination with one another that we saw an increase in productivity here. So we call that co-limitation. Okay, so apparently this community needs both nitrogen and iron in order to grow. And that makes life a little bit complicated to understand why that is. Okay, so this co-limitation, a large area of the ocean is co-limited. The Southern Ocean, I don't doubt, is similar in this regard, and we'll see a little bit of evidence for that tomorrow. And there's three kind of types of co-limitation that can occur. The first is what we call independent co-limitation, and that's purely because the concentration of two resources are being simultaneously drawn down to low levels in the ocean. Okay, so an example of that might be where nitrogen and phosphorus get drawn down together to very, very low levels. You have to add both of them back together to get above their limitation thresholds. The other types of co-limitation are a little bit more kind of interesting, maybe a little bit more complicated. The first is this substitution co-limitation. And this links back to these catalysts that I was talking about. Many of these catalysts, these metals as cofactors, but many of them can actually use different types of metals in these enzymes. So they may substitute one for another, which leads to co-limitation. So for instance, you may be growing in the Southern Ocean, in the Ross Sea, the mixed layer may be very, very shallow. You may have drawn down carbon to very, very low levels. And now you need this enzyme, carbonic anhydride, to convert carbon. And you're worried then about the fact that this enzyme can use either cobalt or zinc. Okay, so you may be co-limited by these elements because this enzyme can operate with one cofactor or another. Another example is that within the kind of light reactions of photosynthesis, we'll see in a second, many of them require iron, but many of them can be substituted for other metals. Okay, and so you can use, instead of cytochrome C6, you can use plastocyanin, which uses copper. So we can generate this dependency between elements purely around the fact that different enzymes can operate with different elements. The other is what we might call a dependency, okay? And so there's a very subtle difference, I think, between these two, but it's worth thinking about it. So the dependency is when your ability to acquire one nutrient is driven by the availability of another, right? So for instance, if you are highly stressed for phosphorus, the most common form of phosphorus in the ocean is phosphate. If you've depleted all of that in organic form, you may want to acquire what's called dissolved organic phosphorus. So this is phosphorus in organic forms. But to do that, you need an enzyme. Okay, you need an enzyme to basically snip the phosphate atom off this complex organic molecule. That enzyme is called alkaline phosphatase, but that needs metals. Okay, that needs cobalt or zinc. So it's possible that your scarcity, if you don't have enough cobalt or zinc, you can't build alkaline phosphatase, and then you are more phosphorus limited. Okay. Another possibility is these transporters that we spoke about. One of the main transporters that phytoplankton use to get iron in the cell uses copper. So if you don't have enough copper, then you can't produce this transporter, and hence you're more vulnerable to iron limitation. Okay, and so we have lots of these interactions amongst elements at the individual level that can be quite complicated to disentangle. And I think in particular, if you want to understand the response of the system to change, we really need to worry about these different acclimatory strategies and what they mean for the community. The last point, I guess, is to make the point that when we measure nutrient limitation, so for instance, these slides, it's all chlorophyll here. Apologies, I've kept the label off the axis here, but this is chlorophyll in milligrams per cubic meter. And so it's possible actually that no individual organism is actually co-limited. But it's just that there's a community of different organisms, that one is limited by iron and one is limited by nitrogen, so that you get this community level co-limitation, okay, that responds. And that may mean that you say, okay, we don't need to worry about co-limitation because actually each individual organism is only limited by a single nutrient. But on the other hand, if we're interested in the impacts of the community and we want to resolve the impacts of the community, then we may need to worry about this, okay? So with this context of nutrient limitation, I want to go back to the Southern Ocean, okay? And so the Southern Ocean, as you see, is all red. If you zoom in very carefully, you can see a little bit of like half shading here that we'll talk about tomorrow. There's a little bit of vitamin B12 here in the Ross Sea that may be important, but by and large, it's limited by iron. These crosses represent the places in the ocean where the iron enrichment experiments have been performed. So that was the Soirée, Sofex, some of the German experiments, Lofex, Isonex-1, Isonex-2, where iron's been added. Hence they're a cross because it's a slightly different type of manipulation experiment. So if you want to worry about NPP in the Southern Ocean, we want to worry about iron, basically. I think that's you would say it's the most important thing. So when I was an undergraduate PhD student, that was what we were all worried about. And the reason we need iron is because it is essential to the light reactions of photosynthesis. So this is more of a biologist's view of the photosynthetic reactions. It's photosystem 2. This absorbs the energy of a photon, gets into an excited state. This energy cascades through a bunch of like redox catalysts, hits the photosystem 1, which is the second photosystem in the chain. It then gets boosted up to a higher energy level, and we cascade through another set of redox catalysts. Okay, that's how this cascading through the catalyst is how the ATP and the NAD pH is produced. And what you see is that every single one of these has iron in it. So this, the QA, the cytochromes are all full of iron. This is where the plasticinin copper iron switch around cytochrome C6 can come in. These are all full of iron. The photosystems themselves are full of iron. Okay, so chlorophyll doesn't have any iron in it. Don't let anyone tell you that chlorophyll has iron in it. Magnesium is the cofactor of chlorophyll. But the reaction center that pigment is coupled to does have a lot of iron. So photosystem 1 has 12 iron atoms in every photosystem. Photosystem 2 has 1 iron atom. So you've got order of 20 odd atoms of iron involved in the photosynthetic process. And this represents roughly 70 to 80% of the cellular demands for iron. They also need iron for respiration, for the respiration process, and for the acquisition of nitrate. Okay, so the Southern Ocean is a very high nitrate system. So if you're acquiring nitrate as a cell, you can't put that to work in your cell until you've reduced it to ammonia. Okay, and to do that, use an enzyme called nitrate reductase. That needs iron. Okay, so we think that the changing iron supply in the Southern Ocean is going to be critical in terms of driving the growth rate changes that we might have seen in the past, that we might see now, or that we might expect to see in the future. Okay, and we'll dig a little bit more process-wise into this tomorrow. I also want to talk about loss processes. I don't know how much these have come up in the lecture so far, but we tend to focus a lot on the kind of what we call the bottom-up factors that modulate the growth rate. But as I mentioned at the start, if you can increase or decrease the total amount of phytoplankton in the ocean, what we call the standing stock, you're also going to affect the amount of NPP that you see. You're also going to affect the type of particles that may go on and fuel the biological pump. And many of these loss processes also are very important in terms of the fact that they can recycle nutrients. Okay, they can bring nutrients from the organic particulate phase back into the inorganic phase. And we know for iron, for instance, this is very important. The first one I want to talk about are viruses. Okay, so much like human viruses can make us stay at home and not travel to places and interact over Zoom, there's a big problem for phytoplankton as well. And they weren't really known about or remarked upon, until really this seminal paper by Jed Furman in the late 90s. And this is what you're looking at is an epifluorescence photomicrograph. And you can see I've marked a kind of protist here, pennate diatoms, and prokaryotic cells, and all these little small dots are viruses. Okay, so the ocean is full of viruses, right? And there's tons and tons of them. And when we measure their, genomic sequencing from expeditions like Tara, for instance, we can find lots and lots of viruses in the system. And to give you a clue as to how important they may be in the system, this is an experiment that was done in the North Atlantic. Apologies for not having a Southern Ocean example. And this is where they've tried to estimate the viral contribution to mortality and compare it to grazing, right, herbivory, which we might have instinctively thought would be the main term. And you can do this in the ocean by doing sequential, what are called dilution experiments, where you dilute the system with seawater of different cutoff sizes. And so you then basically introduce to your phytoplankton the presence or absence of viruses, and you just see how the mortality of your experiment changes. And in the blue bar, you've got the estimated mortality rate due to grazing, and in the red bar, you've got the mortality rate due to viruses. And this is just to show that the viruses are as important as grazers in terms of reducing phytoplankton biomass. What's interesting, I guess, or important to think about is that they may be very different to grazers in terms of what dying, if you're a phytoplankton, you die because you've been infected by a virus, You've lysed, is a process called viral cell lysis, where the cell breaks apart and effectively all the internal parts of the cell are released directly into the seawater. It's obviously very different if you get consumed by a secondary consumer, and then of course their metabolism comes into play. And that's why we're also interested in grazing as a removal agent of phytoplankton and a modulator of the standing stock. And there are kind of a bunch of different processes that we need to think about in terms of grazing. First is this ingestion process. How does the grazer ingest their prey? Do they use filter feeding? Do they use raptorial feeding? There's this concept known as what's called sloppy feeding, which is kind of, I'm sure you all consume your lunch in a very tidy manner. But some zooplankton, when they consume, they don't actually ingest all of the prey that they try to consume, and some of that gets released. And so you may ingest this amount of POC, organic carbon, but the amount of carbon that gets into the biomass of the grazer is going to be roughly reduced by about 10-15% because of this eating mechanism. Of that carbon that gets into the zooplankton, parts of that will be allocated towards the growth and reproduction, and parts of it will be consumed by respiration of the organism and by what's called excretion. And this excretion process is interesting because nutrients are released along this process pathway as well. And obviously, if a zooplankton is performing a lot of respiration, a lot of excretion, it's going to have what's called a very low gross growth efficiency. Right? So the growth efficiency is effectively how much of what you eat actually ends up in your biomass to produce new zooplankton. And then finally, we get this process known as egestion, which is the fecal material. You might have heard of fecal pellets. These are packaged, very dense, fast-sinking parts of the egestion from the zooplankton. And so these are really important in terms of understanding, what gets taken from the seawater into the phytoplankton, then is processed by the ecosystem, okay, either zooplankton or bacteria. Some of that ends up in their biomass, some of it gets packaged up and exported into very fast-sinking particles, and some of it gets remineralized back to fuel more productivity in the system, okay? Let me check how we're doing for time. Okay, great. So if we want to understand what's going on with productivity, we need to think of a bunch of different factors, right? We've got these, what we call bottom-up processes, temperature, light, nutrients, that may affect the growth rate. Then we have from the top down, we have these grazers and other mortality feedbacks that may affect the standing stock. And then we've got the product of the two, the growth rate and how many phytoplankton you have, that sets the overall rate of net primary production, okay, that you might be interested in for a variety of reasons. I want to end by talking about what we know about the projections of net primary production, how we think this key process that links chemistry, biology, and some physics, how that actually might change in the future, and come now really down into the sort of Southern Ocean, the region of interest, to set the scene a little bit for tomorrow. Okay. So to make projections, we use models, as Jens mentioned in his presentation. We use these global scaled coupled climate models. This is a really nice web page. If you go here, Carbon Brief, how do carbon models work? It's a really nice article that talks you through the sort of historical evolution of the climate models and where they've been and where they're going. What this shows you is basically when different types of models were developed, in what decades, and at what stage they were integrated into the kind of Earth system models that we use to make forecasts today. So you can look at this and find your favorite thing. You can see ice sheets came in relatively late, as did marine ecosystems. Marine ecosystem models existed for many, many years, but it took decades for them to become integrated into the global climate models. On the other hand, the carbon cycle or the atmospheric chemistry came online much earlier. Okay, so before we look at the MPP, I want to just show you, what we see in terms of physical variables in the system. Okay, so this is sea surface temperature. These are projections of SST changes for the CMIP-6, so this is the Coupled Modelling Comparison Project, the 6th phase. These SSPs are the different climate scenarios. bigger number, bigger radiative force in 2100. These show you the CMIP5 kind of analogous, but let's focus on CMIP6 here. And this is effectively the surface average SST compared to a reference period. The solid line is the multi-model mean. The shading represents the spread of the models, okay? And so what we see firstly at the global scale, we see for SST, we see this really clear separation into scenarios, right? The main thing that dictate the SST at the end of the century is really the scenario that we end up on, okay? And then the multi-model spread is quite small, right? We can clearly pick out the green, the blue, the red. And this is really clear information for policymakers, right? Putting that IPCC hat on. And the more carbon we emit, the higher the climate change scenario, the higher the SST will be. This maps out at regional scales, right? And so here there's a measure of kind of model agreement. It's kind of stippling. So the stippling is where the models agree, and this stippling effectively, it's quite a low bar for model agreement. It's basically the majority of the models agree in the sign of the change, okay? So unsurprisingly, the ocean gets warmer, all models can agree that it gets warmer. It gets even warmer at the higher emissions scenario. Okay, and the reason I'm showing you this is that we can contrast this to what we see for net prime production now. Okay, so this is the same subset of those models, right? But still a fair few, tens of models. And now we see a very, very different picture, right? The global scale, we now can't pick out the scenarios as clearly as we could for temperature to contrast it with this, because the multi-model spread is now so large that it's swamping the scenario variability, okay? To the point at which the multi-model mean for many scenarios is near zero, plus or minus a very large standard deviation. Okay, the reason that exists is because none of the models really can agree on the directionality of change. So if we look here, this is the low emission scenario, SP126, or even at the high emission scenario, 5A5, we see very little stippling, okay? What that means is that most of the models don't agree on the sign of the change. Okay, so this presents a very different message to a policymaker. This says that basically I can't even tell you if productivity is going to go up or down in the future. Okay, so that's really stark level of uncertainty. We see similar things for other aspects of the biological system. We won't worry about that. And you might even argue this doesn't even represent probably the true uncertainty, because actually many of these models are actually very similar, and they all simplify many aspects of the marine system. If we look at regional scale, the story doesn't really get any better, right? So this is a regional analysis of different biogeochemical provinces. So now the global's down in the corner here. And what we can see is that there are, some regions where the uncertainty is enormous relative to the global uncertainty. So on the previous slide, you might have been struck by the global trend. So sorry, if we go back to this slide, you may have been struck by the fact that this envelope is enormous, okay? But if you look at different regions, that envelope can be 4 or 5 times higher, okay? So for instance, if you go to the Atlantic subpolar gyre, we may agree that productivity is kind of going down, but the 1 sigma uncertainty, which is a relatively conservative estimate of uncertainty, can't really tell us by how much things are going to go down. If we look at some key regions like the equatorial Atlantic, the Indian Ocean, North Pacific subtropical gyre, South Atlantic subtropical gyre, again, we can't constrain the sign of the change, and the regional uncertainty is perhaps double or triple what we see at the global scale. So we've got a real problem here. The contrast is actually the Southern Ocean, okay, which is maybe what we're all worried about. And you can imagine we spend a lot of time trying to worry about what the equatorial Pacific, why it's uncertain, or why the Indian Ocean is uncertain. I'm not sure that's much of interest maybe to this audience. So let's look at the Southern Ocean. And actually the Southern Ocean presents a really unique trend in the fact that the NPP is projected to increase, and the models seem to be relatively confident. If we go back to this slide again, you can see it's one of the only places where there's any stippling on the map, okay? So this perspective that the Southern Ocean is becoming more productive with climate change is very, emerges a very high consensus from climate models, okay? And that presents, again, an interesting message for policymakers. It suggests that we have a good understanding of what's happening in the Southern Ocean, right? That we project that the Southern Ocean is going to become more productive, more fertile. The analysis of this is basically because more iron is coming in from the to the Southern Ocean from various means, and that's fertilizing the growth rate, as we saw, which is leading to higher levels of net primary production. And yeah, okay. So I'm going to stop, and we're going to pick this up tomorrow. But before we do so, I wanted to give you some kind of take-home messages. Firstly is that net primary production is maybe the critical carbon flux in the Earth system. If we want to understand what's going on with it, we've got to worry about some nitty-gritty of chemistry and biology. We need to understand how the changing nutrient requirements and nutrient availabilities and all these complex loss processes linked to things like viruses or even larger things like krill may come into play. Iron is unusually important in the Southern Ocean, so that's interesting, or you could say annoying, because it's an element that has very complex chemistry. It's a very short residence time, and so there's it's not so easily controlled by the physics. And lastly, that the projections that we have now from our best available models suggest that the Southern Ocean is going to become more productive due to climate change, and that these models have relatively high confidence. This is the message we saw at CMIT 5 as well. So the last kind of 10, 15 years, it's been quite a clear message coming out of the community. So tomorrow, we're going to dig into that. We're going to assess whether we are actually as confident as the models are in terms of these projections of NPP in the Southern Ocean. In doing so, we're going to look really into some more unique processes and unique aspects of the Southern Ocean and what makes it actually very different from a biological perspective to the rest of the world ocean system. And with that, I think I'll stop if we haven't gone on too long, and I'm happy to answer any questions that you might have.